Good morning, everyone. It's my great pleasure to be here to present you our research findings. And in fact, we are a team from Paris Tech Shanghai Jiao University. And our topic is a multi-user 360 video streaming system for wireless network. And I will give my presentation in these four parts. First, the background and our work, our experiments and results, and finally, a conclusion. So let's start with the background, and I would like to show you this picture. I think this is a common disappointment we encountered when we are watching an online video, and we have to wait for the lifetime until the video can start playing. So this is a heartbreaking thing, and we believe that this is partly because of the limited bandwidth and latency, and especially in a 360-degree video transmission, because the size of this kind of video should be 4 to 6 times the pixels of a regular video frame. And we can see from the picture that the blue bar is the 360-degree video occupation, and the green bar is the regular video. And yeah, we can see a very occupied bandwidth. And there's another problem, which is the redundant viewport transmission. For us users, we just use about 20% of the sphere to get the viewport, but the network has to transmit the entire sphere in order because the network doesn't know if the head orientation of the user will be changed or not. So there are some prior works that focus on dealing with those problems. First is a method provided by Chen in 2016, which is based on pre-segmented tiles. He did a pre-segmentation on the video to just transmit the visible part of the video to release the burden. And then there's another method by Byung in 2017, which is based on quality emphasized region. This method will lower the quality of the invisible parts of the video to make the bandwidth less used. And for our work, we went one step further. We designed a multi-user 360 video streaming system on wireless network. And the data flow is as shown in this picture. First, the head-mounted display device will get the head orientation data from the user, and then it will transmit to the server. And the server will record this data and do two predictions. First is the conjoint viewport prediction, and then the head orientation prediction. And the 360-degree video data will be divided into the unique view and the conjoint view. And the unique view will be unicasted to the corresponding clients, and the conjoint view will be multicasted to all the related clients. And the conjoint view can be transmitted only once, so that we can save bandwidth. And there are two important parts in our work. First is the head movement prediction, and why we do this, because there's a delay of transmission between the request sent by the user and the data received by the user. And the delay should be 20 to 300 milliseconds. So we did our prediction interval at 100 milliseconds after a request sent. And this aims to eliminate the difference between the changement of head orientation and the data of video. And in this model, our input should be the user's head orientation during a period of time in past, and the output should be the user's head orientation after the time delay. And we use two models. First is the linear regression, which is easy to implement and work fine for short time delay. And then we use also the long short-term memory to because it is quite efficient for dealing with sequences, especially in our situation, the data are the time series data. And the second part is the conjoint viewport prediction. We first define the viewport, which is the region of a video frame which is visible to multiple users at a given time. And then this part will be transmitted in public channel by multicasting, so that we can transmit only once the conjoint part. And the input of this model is head orientation of all the users during a time period in past. And the output is a binary classification, whether there's a conjoint viewport among the users or not. And we also use the long short-term memory to do this. And then we applied our structure on some data sets, and it is provided by Gorbion, which is called a 360-degree video head movement data set. And this data set contains the head orientation data of 63 viewers watching 7 different video clips. And the data are recorded 30 times per second in the format of quaternion. And we converted the quaternion into Euler angles for our use. And we did the prediction after 100 milliseconds. And here are the results of our prediction. We defined 2 indicators to measure the error. First is the root mean square error of the angle. And then there's a failure rate, which represents the percentage of prediction with error more than 10 degrees. And we can see from here that yaw is more error prone because the users tend to move their head more often in the horizontal directions. And we can also see that the long short-term memory performs slightly better than the linear regression, but not much. And we believe that this is because the head movement is linearly correlated in short term. And for the results of the conjoint view model, we applied it only on 2 users to see the performance. And we defined a threshold theta, which is the maximum angle. And this angle defines a conjoint area. For example, the 70 degree means that we can judge that there is a conjoint viewport under 70 degrees of the difference. And we call our model a one-step model because the model will judge if there is a conjoint viewport. And in comparison, we did another method, which is called the naive method. It will first predict all the head orientations of all the users, and then calculate the difference of the angle, and then do a manual judgment whether there is a conjoint viewport or not. And we can see that the one-step performs slightly better than the naive method. And here are the results of our conjoint proportion estimation. The yellow line is the conjoint view portion during the whole play. And we define the proportion by using the conjoint viewport area divide the field of view of the user. And we can see that the conjoint proportion during the whole play is generally high, which is because the users tend to have a similar, the similar region of interest. And we can conclude that it is feasible to save bandwidth by multicasting the conjoint viewport. And here are, and finally, how much bandwidth we've saved. In this table, we defined the percentage of bandwidth saved as this formula, and we applied it on 5 different video clips. And we can see that bandwidth is saved from 9.6% up to 28.7%, which we think that is a noticeable economization of bandwidth. As a conclusion, first our research focused on the 360-degree video transmission optimization, and then we used the linear regression and long short-term to do the head orientation prediction, and then we used the long short-term memory to do the conjoint viewport prediction. And as for the results, we can see that the precision of prediction is relatively high, and there's a noticeable bandwidth saved. And due to the time limit, we haven't finished our experiments yet. And in the future, we are focusing on users more than 2. And also, we will apply our models on different prediction time intervals. Yeah, that's all about our research. And if you have any questions, please be free to contact us. And thank you for your attention.
Again, very good timing. Thank you very much, Nan.